On the topic of prediction, data science is often used to make predictions about the future. If we are trying to predict an outcome for a particular individual, for example, how she will respond to a treatment or whether he will buy a product, it's natural to base the prediction on the outcomes of other similar individuals. The table below is adapted from a historical data set on the heights of parents and their adult children. Each row corresponds to one adult child. The variables are a numerical code for the family, the height in inches of the father and mother, the number of children in the family, as well as the child's birth rank. 1 is associated to the oldest child, sex to be male or female, the height in inches. So let us take a look at the table here. Our data are stored in family_heights.csv file. A primary reason for collecting the data was to be able to predict the adult height of a child born to parents similar to those in the data set. Let us try to do this by using the simple average of the parent's height as the variable on which to base our prediction. This parent's average height is our predictor variable. In the cell below, its values are in the array parent_averages. The table heights consist of just the parent's average heights and the child heights. We're going to take a look at a scatter plot of two variables to find an association between them. So we look at these two columns, the parent average and the child height. We can look at the data and try to analyze this, but what is the visualization? For those of you who are interested in the breakdown of the code, the breakdown of the code is demonstrated here. For example, the first line basically calculates the average height of the father and mother, add them together and divide by 2, and then table creates a new empty table. The table class is part of the data science library, as you learned before. Dot with underscore columns method is used to add columns to the newly created table. And then we have the parent average, which is the name of the first column being added to the table. And finally, we have the parent_averages, which is the averages that we calculated up here. The question is, what is the relationship between a child's height and the average parent's height? Let us make a scatter plot and see how we can relate these two variables. In the scatter plot, on the horizontal line, we have the parent average height and the child's height. This is our scatter plot. So it seems like we can fit an increasing line, and we see a correlation between x and y. Later on, we're going to calculate the correlation coefficient, the coefficient of determination, to have a better analysis of this data. Suppose the researchers encountered a new couple similar to those in the data set, and they wanted to know how tall their child would be. What would be a good way for him to go about predicting the child's height, given that the parent average height was, say, 68 inches? One reasonable approach is to base the prediction on all the points that correspond to the parent average height of around 68 inches. The prediction equals the average child's height calculated from those points. For now, we just make a reasonable definition of what around 68 inches means and work with that. Later in the course, we're going to examine the consequences of such choices. We'll take close to mean within half an inch. The figure below shows all the points corresponding to a parent average height between 67.5 inches and 68.5 inches. These are all the points in the strip between the red lines. Each of these points correspond to one child. Our prediction of the height of the new couple's child is the average height of all the children in the strip. That's represented by a gold dot. So let's take a look at our visualization. So the breakdown of the lines of the code here are as follows. For example, heights.scatter, it basically creates a scatter plot with data from the height table, the parent average, this one that we calculated before. For example, plots.plot 67.5 and 67.5 and 50 and 85 basically adds a vertical line to the plot at x equals to 67.5, representing the average height of the parent in this case. The y coordinates are between 50 and 85. The color is red, and the line width is set to be 2. So these two are your vertical lines. Finally, plots.scatter 68, 67.62 with color gold and S40. This line adds a single scatter plot point at the coordinates 68 and 67.62, where 68 represents the average parent height and 67.62 represents the predicted or actual height of the child. We set the size of the dot to be 40. In order to calculate exactly where the gold dot should be, first we need to identify all points in the strip. This corresponds to the row where parent average is between 67.5 inches and 68.5 inches. Let's take a look at the line of code here. We have the parent average and the child. Close to 68 is defined as the heights where the parent average are in between 67.5 and 68.5. The predicted height of a child who has a parent average height of 68 inches is the average height of the children in these rows. That is 67.62. For example, if we use NumPy average, we see that it is 67.62, and that's how we do the calculation. Now, we have a way to predict the height of a child given any value of the parent average height near those in our data set. We can define a function predict_child that does the same thing that we are looking for. The body of the function consists of the code in the two cells above that. We're going to just put it here. We define our function, predict_child. P_average is your argument. It predicts the height of a child whose parents have a parent average height of P_average. The prediction in the average height of the children whose parent average height is in the range P_average plus or minus 50%. Given a parent average height of 68 inches, the function predict_child returns the same prediction, 67.62 inches, as we got earlier. The advantage of defining a function is that we can easily change the value of the predictor and get a new prediction. For example, if you pass in 68, your function generates 67.62. If you pass in a different value, like 66, the function generates 66.0, 86, 40, and the rest of the data. The question is, how good are these predictions? We can get a sense of this by comparing the predictions with the data that we already have. To do this, we first apply the function predict_child to the column of parent average heights and collect the result in a new column labeled prediction. Now let us apply predict_child to all mid-parent heights. Remember that the line of the code here, with_column, this method creates a new column in the heights table. In this case, a new column called prediction is added, and it contains the predicted child height that we calculated before. The predicted heights are stored in the prediction column. Now, if you look at the line of the code here, heights with predictions, we have the parent average height, the child height, and the predicted value for the height. Well, as you can see, you have differences. You have some residuals, 73.2 and 70.1, 69.2 and 70.1. As you can see, there are differences. Some of them are lower than the actual value, some of them are higher than the actual value. To see where the predictions lie relative to the observed data, we can draw overlaid scatter plots with parent average as the common horizontal axis. So heights_with_predictions, the scatter plot looks like this. On the horizontal line, we have the parent average height, and on the vertical line, we have the child. The graph of gold dots is called a graph of averages because each gold dot is the center of a vertical strip like the one we draw before. Each one provides a prediction of a child's height given the parent average height. For example, the scatter plot shows that for a parent average height of 65 inches, the predicted height of the child would be just above 65 inches. And indeed, predict_child 65, evaluate that as 65.84. Notice that the graph of averages roughly follows a straight line. Later on, we're going to talk about the regression line or the line of best fit and do the calculation separately. This straight line is now called the regression line as it is one of the most common methods of making predictions. The calculation that we had just done is very similar to calculation that led to the development of the regression method using the same data.